All right, let's jump right in. We're going all the way back to 1957 to look at a paper that honestly changed everything about how we interact with computers. It's about a project called FORTRAN, and it's really the story of how we first taught machines to understand a language that looked a lot more like our math than their ones and zeros. This was a huge deal.
So, to get why Fortran was such a game changer, you first have to understand the problem. And this quote from the paper itself just says it all. See, back in the early 50s, computers were lightning fast at doing the math, but telling them what to do was agonizingly slow. Think about that. Over 90% of the time you spent on a problem was just the humans trying to write the code. And this all led to what you could really call a programming crisis. You had these incredible new electronic brains that could change the world, but they were being held back by this massive human bottleneck. The progress of science and engineering was basically stuck in traffic, all because programming was an absolute nightmare.
This chart really puts the cost into perspective, doesn't it? The paper pointed out that about 2/3 of the money spent solving a problem went into just getting it ready. The actual time the super-fast computer spent working, just a tiny fraction of the whole effort. It was a wildly inefficient system, with the most powerful tool in the room just sitting idle most of the time.
And this analogy just perfectly captures how painful that whole process was. Imagine trying to talk to someone, but for every single word you want to say, you have to stop and look it up in a dictionary. That's exactly what programming was like. Every tiny step, every simple add this to that, had to be manually translated into the machine's bizarre numeric language. It was incredibly tedious and, as you can imagine, absolutely riddled with errors.
So, how do you solve a crisis like that? Well, a team at IBM came up with a pretty radical idea. What if, instead of forcing people to learn the machine's language, we taught the machine to understand ours? What if we could build a system that let the computer do all that heavy lifting itself?
And that was the mission. That was the whole goal of the Fortran project, which kicked off in 1954. The idea, as they put it, was to let programmers write in a concise language like that of mathematics. But here's the key part: automatically produce an efficient program. They didn't just want a simple translator. They wanted the computer to write code that was just as good, or maybe even better, than a human could. And look, this was a massive undertaking. From the summer of '54 to February '57, it took about 18 man-years of intense work to pull this off. But by the end, they had it: a brand new language and the translator program that was the key to the whole thing. And this is so important. They had a specific, measurable goal. This wasn't about making a small tweak. They wanted to take the hardest part of the job, the coding and the endless debugging, and reduce it by a factor of 5. They were shooting for a full-blown revolution in how work got done. Okay, so how did they actually do it? Well, the whole system really boiled down to two brilliant components. First, you had the Fortran language itself. And second, you had the translator, this incredibly complex program that acted like a universal interpreter between the person and the machine. And this right here, this is the aha moment. On the left, you see the good old quadratic formula from math class, and on the right, the Fortran code to solve it. It's almost the same. For the very first time, scientists and engineers could write instructions that looked and felt like the math they already knew. It was just incredible. And the leverage this gave you was just immense. For every single simple statement a programmer wrote in Fortran, the translator could spit out anywhere from 4 to 20 lines of detailed machine code. I mean, that's an incredible force multiplier. It just automated away thousands of tedious little steps. Now, the translator program was a marvel of engineering. The paper breaks it down into this complex 6-section process, but you can basically think of it in 4 big steps. First, it would read and figure out what the human's code was trying to do. Then, it would handle all the complicated stuff like loops. After that, it would stitch all the pieces together, and finally, it would assemble the finished, ready-to-run machine code. So, the theory was sound. The engineering was brilliant. But the million-dollar question remained: did it actually work in the real world? The team had high hopes, but I don't think even they were prepared for just how well it would work. And I just love how the authors introduce their results with this great touch of academic understatement. They basically say, hey, we know one example isn't proof of everything, but nevertheless, here are the facts. And wow, those facts were something else. So they tell this story. They took a programmer, gave him a pretty hefty job to do. He went to a one-day course on Fortran, spent a couple more hours with the manual, and then wrote the entire program using just 47 simple Fortran statements. The computer then took his code and, in just 6 minutes, translated it. And get this, those 47 lines of code, they expanded into about 1,000 lines of machine instructions. Now, the first run had a bug. But because the programmer was looking at his own 47 lines of simple logic, not 1,000 lines of gibberish, he found and fixed the bug almost instantly. Debugging went from being this impossible nightmare to just a manageable task.
So let's just put this side by side. The programmer estimated that to do the same job the old way, by hand in raw machine code, would have taken him about 3 full days. That was the baseline. And with FORTRAN, he did the whole thing, from writing the code to fixing the bug and getting a working program in just 4 hours. Think about that. From 3 days of painstaking work down to half a day. This wasn't just an improvement, it was a completely different universe. And that's the real takeaway here. The revolution wasn't just about speed, it was about accessibility. FORTRAN democratized programming. For the first time ever, it was actually easier to teach a scientist how to use FORTRAN than it was to teach them the computer's own arcane language. It threw the doors wide open for a whole new generation of people. And that really brings us to today. The journey that began with FORTRAN, this idea of teaching machines to understand our logic, our language, has led us to this absolutely extraordinary moment. For over 60 years, it's been a one-way street. We talk, they listen. But now, with things like generative AI, they're starting to talk back. And it leaves us with one heck of a question to think about.